Welcome to a lesson with Dr. Powell. We are continuing the last video where we were thinking about calculating the centroid of this region here, going from 0 to 2 in the x. This goes from 0 to 1 in the y. And in order to make that calculation, we need to figure out what the total area is in here. So we'd have to compute this integral. In order to compute this integral, we might look at a trig substitution, thinking of this as a Pythagorean theorem type idea. So with a hypotenuse of 1, one of the sides being x over 2, and the other side being the square root of 1 minus x over 2 quantity squared. Now this looks like a sine cosine type triangle, so we'd let that be sine, cosine, and 1 is just 1 there. And so this integral would then turn out to be the integral with a cosine. So this part right here just becomes cosine. Then you need to know what dx is. So x is equal to 2 sine theta. So that dx would be 2 cosine theta. So we put the 2 out here, and times cosine theta makes that a square with a d theta. So using trig substitution, we get to here. We could change bounds here, if we will, and if we think about it. When x is 0, sine will be 0, and on the interval that we're looking at for for thinking about how we have to restrict sine, so it's a one-to-one function, so we only get one value of theta out. The restriction of sine as a one-to-one function in order to have an inverse is actually from negative pi halves to pi halves. So we're going to be just taking things in that interval as we output angles, and just keep that in mind. So as we go, let's see. So we're going to have 0, because when x is 0, sine is 0, so the angle will be 0, and the y value at 0 is just 0. And then when x is 2, this is going to be 1. So when is sine of theta 1? It's at pi halves. So we're going from 0 to pi halves. So this is our integral. And this will compute our area. So we never have to translate back to x anymore, because we just transferred our bounds. From 0 to 2, we turn into 0 to pi halves, because we put x value of 0, put it here, and saw that sine was 0, so theta must be 0. Then when x was 2, we noticed this was 1, is equal to sine theta, so theta must be pi halves. Okay, now we can use an identity for cosine squared, which is cosine 2 theta plus 1 all over 2. This is still in the integral. We just use a trig identity. We did not take any antiderivative. This is nice because those 2's cancel. Okay. Next we have, let's see, cosine of 2 theta plus 1. So on this part right here, okay, we can take an antiderivative of cosine of, see here, and let's see, cosine of 2 theta. And also we can kind of think about what's happening with cosine. So cosine looks something like this, and normally it goes from here to here in pi halves, but we're going twice as fast, so we actually go from here to this point. So in reality, it looks like that this part will go away in the integration because of symmetry. We're going to get an integral of net area of 0 if we integrate just the cosine 2 theta part. So really we'll just be left with this part. But let's just verify that by taking antiderivative and see. The antiderivative of cosine 2 theta would be sine of 2 theta over 2, and you can double check it. Taking a derivative here, you do get back to cosine 2 theta. Okay, so then if we just did this part individually from pi halves and 0, let's see what happens. So if we plug in pi halves, we get 2 times pi halves, which is just pi, and the sign of pi, the y value there is just 0. And then when we plug in 0, we also get 0, so we get 0 minus 0, which is 0. So which confirms the notion here. Sometimes before we actually tackle trig part, if we have bounds, it's nice to kind of see if there was some kind of symmetry, if we can cancel it out. In this case, we can. So this part actually can be thought of as non-existent. So really all we're integrating is just this 1, and the 2's get canceled, so just 1. So, so we end up just getting theta, and we're going from 0 to pi halves. Sometimes you can just think of this as a rectangle of height 1 of that interval. It's just the length of the interval, if you will. So we could have just said the integral is pi halves. So we're actually getting that the total area in here is pi halves. That's the total area. So the total area is equal to pi halves of this shape. And now we can use that fact, okay, when we go to compute our centroid or x-bar value. Okay, so let's keep this in mind. It's pi halves. Now let's actually look at the integral that we have. So remember that what x-bar will be. It's 1 over the total area, so 1 over pi halves, times the integral from 0 to 2. That's this x interval from 0 to 2. Of, now remember x, we're taking the average value of x as a function, but then with respect to m, so we need to put in dm here. What is dm? Dm is simply the area of a little rectangle right here, right? A little bit of area, because dm is like dA. It's just the rectangle area, so it'll have a dx times the height here. So dx, but then just times the y value, and this function right here was the square root of 1 minus x over 2 quantity squared. Okay, so this is how we compute it, right? And we know it's 1 over the area, so we had to compute 2 integrals in order to get x bar. This part, so 1 over pi halves, that would just be 2 over pi. Okay, we just take the reciprocal. And then here, let's do a little u substitution. This part right here, let's call that u. And let's think about what the derivative of u is. Du dx is equal to, so this is like 1 minus x squared over 4. So that would be minus 2x over 4 is equal to minus x over 2. So minus x over 2 is the derivative of u with respect to x. So in making the substitution, we can cross out this dx and replace it with du divided by this derivative, which is negative x over 2. Notice that this x will cancel with this x down there, and we'll have negative a half, which will come out to be negative 2 on the top. So, so we'll end up getting, and I'll just put this right here, negative 2. Okay, now the negative will be taken care of because of the bound, because of how things will happen in the bounds. See, when x is 0, u is 1. When x is 2, this is a u value. When x is 2, then u will be 0. All right, and then we just have a square root of u here, du. So this is how it relates. Now, see this negative and this 1 to 0? Well, we can switch it to 0 to 1, and will make that a positive. And we'll end up getting 4 over pi integral from 0 to 1 of the square root of u du. Let's just double check to make sure we did all this correctly. Let's see, negative, okay, so u is equal to negative a fourth times x squared, right? And 2x, yep, negative x over 2, we divided by that, and that cancels negative a half, negative 2. Okay, so I think we're pretty good here. I just wanted to double check. All right, now here, this will become u to the 1/2, use the power rule, becomes u to the 3/2 divided by 3/2. And that's multiplied by 4 over pi, and that'll become, okay, and that'll become 8 over 3 pi times, okay, and this is going from 0 to 1, right? So 8 over 3 pi times u to the 3 halves as we go from 0 to 1. And this is going to be the same as if we just plugged in 1 here, because plug in 0 to 0. So we end up getting 8 over 3 pi. So we just computed what x bar is. X bar is equal to 8 over 3 pi. Now, in the next video, we will focus on what y bar is. Thanks for watching.